And now I want to tell you how multiple beam interference relates to one of the most important inventions of the 20th century, the laser. All right, so you know laser stands for light, it's an optics class, amplification, by the stimulated emission of radiation. I never noticed that light and radiation are in there. And I also have a book on my bookshelf that I bought only because laser was spelled with a Z, and it's an actual technical book. Couldn't believe it. Okay. So let's talk about what's really happening in a laser. And this is going to be qualitative. We're not doing the Seelig book here. But first of all, so we know what light is. We know what amplification means. But let's see, how does this amplification occur? And what is stimulated emission? Let's see what that is. So we can't really do this with waves. Okay, we're going to have to actually acknowledge that things are happening inside a material, optical processes. So this is energy. Okay, so we need a little chemistry class here, that electrons can exist in different states, right, inside a material. So it can be chemistry or solid state physics. So say you can be down here in E1, or you can be up here in E2, okay? Don't worry, it's not electric field, we're not gonna get complicated. This is the ball sitting at the bottom of the hill, this is the ball sitting on the top of the hill, right? Just energy levels is all they are. And the electrons, we know they like to sit around, because they're lazy, they like to sit in the low electron energy levels, but then one might decide, okay, I'll hang out in the higher energy level. You might have some distribution like that. You get a Boltzmann distribution, basically. Statistics tells you, based on your energy, in our case, a lot of them are here, because this is the ground state, and less are up here. So this one can go through spontaneous emission for no reason whatsoever. It can jump from this level down to this level. Well, it has more energy here than here, so to get rid of the energy, it emits a photon, right? So spontaneous emission is just when the electron jumps from E2 to E1, ditches the energy as a photon, which we'll call h bar omega, because you may know for photons, the energy of the photon is related to its frequency and Planck's constant, okay? So that is spontaneous emission. It just happens. And it has some probability depending on the properties of the whatever's creating this two-level system. You can also have a case where, this maybe is more familiar, you have a bunch of electrons sitting down here and you send in a photon, h bar omega, and one of them says, I shall partake of that photon, and it absorbs it and it jumps up to here. Right? And then the photon is gone, right? The light got absorbed, and that is stimulated absorption. All right. So you can see this one was spontaneous. We didn't put in any light to make it happen. It just happens at some rate. There's some probability for that to happen. You get a photon. Here, we caused it to happen. We sent in light, and it really made that happen. Let me draw it closer. Really makes it happen. But then here's the weird one, right? Actually, stimulated emission is sort of the weird case. Say you have one sitting up here and a bunch sitting down here, and by me electrons, right? And we said you can have spontaneous emission. There's some probability that will happen. There's some rate depending on how many there are, how long you wait for one to go down. But if you send in light, h bar omega, and all these frequencies, all these energies match the difference between E1 and E2. So that's the important part, is that h bar omega equals E2 minus E1, that difference. So sort of a resonant frequency. So if you send that in, even though it can't absorb it, it encourages it to go down, okay? And when it does, you get the original photon, plus the energy has to go somewhere, so you get an identical photon. So you send one in and you get two out. Okay, we still conserved energy, right? It went from E2 to E1. Nothing bad is happening, but it is a little bit weird, right? It just sees what it could make, so it makes one. So that is called stimulated emission. And when this was first thought about and discovered, it was sort of phenomenological, but now we understand it at a much more deep quantum level, the reason these things happen. So another thing you could think about is that the probability, so what we'll just say here is where you can get gain, right? So we're trying to do light amplification by the stimulated emission of radiation. Clearly this is where it's at, right here. We send one photon in, we get a second one out, an identical second one out. So that's what we're trying to do, okay? So the probability of stimulated absorption equals the probability of stimulated emission, okay? So they are equally likely under identical conditions. The electron sits here, it sees the same density of photons and everything. That's just as likely as that. So it goes up, it goes down, it goes up, it goes down. But the rate of stimulated absorption in this simple picture is much greater than the rate of stimulated emission due to the Boltzmann distribution. Okay. And that's physics we haven't talked about. That's basically just saying you have a lot more of them down here. So if you're talking about the rate of what really happens, well, this happens a lot more often. If you just shine light, you're not going to get gain because a lot more of your light is going to get absorbed than is going to get amplified. And that's simply because you have more here than you have here. That's the only reason, okay? So what you need to do is get more up here, right? So, okay, shine light harder, shine more light, let's shine a lot of light. We get a lot of stimulated absorptions up here. And then a lot of stimulated absorptions, oh, you get faster stimulated emission. Well, you just screwed yourself, basically. So you shine light harder and you get more up here, oh, they go down faster, right? In the end, the best you can do is sort of 50-50, right? If you shine infinitely hard light, what you ultimately have is half here and half here. You can reach sort of a 50-50 point with equal rates of light going up and down, and you're shining your light and you're getting no gain, right? The light just kind of goes through. So you can't get gain with two levels, all right? So the trick to get gain is to use a third level. To have gain, which by that I mean to get some sort of amplification from that stimulated emission, is you want to have your E1 and your E2 kind of like that, and then you want to have another one in here, E3, like that. All right? So let's see. So then what could you do? Then you could pump at E2 minus E1. And you can pump really hard, right? So at typical Boltzmann distribution then, you'll have a bunch down here. You might have a few in E3 and just maybe one in E2. So then you pump it really hard with photons that match here. So you get a bunch of stimulated absorption and you get a bunch of stimulated emission between these two. Maybe you pump so hard you get these to 50-50. This is all just ideas, right? None of this is what really exactly happens. You don't get to 50-50. But anyway, what you end up getting, this important thing here, is you get a population inversion. You pump on E1 to E2 to get a bunch in E2, and then you end up with more in E2 than E3. And you can pull it off with this third level because you're not pumping on this level. And then it just rains electrons. And they make photons. Right? Well, I'm sorry. So you make your population inversion, and then you send in one photon, and it stimulates two photons. Right? And then maybe those two stimulate another one to come down, and you get four, etc. So you can get gain, right? So population inversion can give you gain, and the way we've drawn it, and E2 minus E3 for photons between E2 and E3. You send one in, and there you go. So how does this actually work in a device? So let's imagine if we had this idea, how we would really make this. What would it do? So, a rudimentary laser might look something like this. You have your gain medium. This would be called. It can be a lot of things. And it's kind of your three-level system, right? Your E1, your E2, and this intermediate level. And then down here you might have like a flash lamp. It's the old-fashioned way. This has all been completely replaced by semiconductors, by the way. Most of them don't work this way anymore. So the flash lamp is a bunch of just really bright UV light, and it basically creates the inversion. Right, so you get a bunch of electrons there and a few there. And then I guess you could send in your input, right? I naught, and you'll get a bunch of gain to the population inversion, and you'll get you'll get gain times I naught. Right? So technically, that is a laser, right? Technically, we have light amplification by the stimulated emission of radiation. We've done it, that's a laser. But that's not a laser, okay? If you think about it, if you send light in, say for every photon you send in, you get 10 out. Okay, that's fine, that's gain. But this is lacking a lot of the properties that we think of a laser. You think of a laser as being highly coherent, right? Coherent means all the photons will have sort of the same phase when they come out. And this process of stimulated emission does make an identical photon, but they're going to be identical to what you send in, right? So if your gain is 10, then you know they'll be coherent in groups of 10. But if your light going in isn't coherent, your light coming out isn't really going to be coherent either. So it's not coherent. And also, you think of it as laser as being highly collimated. Right? No, there's really nothing collimated about this. If you just send light into this material and it's not highly collimated going in, and it makes identical photons in the gain medium, it's going to be similarly uncollimated coming out. Right? So there's nothing really special here. We have gain, but we don't really have the special properties of a laser. So here's the trick. Let's see. Oh, good. There's an empty board here. So let's redraw. Here's our flash lamp. And here's our gain medium with the 3 levels like that. And the final thing you need is multiple beam interference. You need to put the whole thing inside of a resonant cavity. So we talked about the electric field, this being sort of having sort of a normal mode of the electromagnetic field for light. If you think in terms of photons, what it means is a photon likes to stay in here. A photon bounces in its phase, adds up coherently, it's constructive interference. So a photon will stay in for many, many bounces before it goes out. Okay? So if it's high finesse, it'll stay in here. So what that means is once you have your population inversion, then a photon of the right frequency is in there, and it creates 2, and they're identical. But they're also on a certain mode of this resonant cavity. So when they bounce off and come back, they're in the exact same mode, the exact same direction, the exact same K vector and everything, and they make 4. And then they bounce and they come back again, and they make 8. So you don't even have to pump it really, just once you get it going, it creates a huge amount of light, and then just a little bit leaks out. You put a little hole in your mirror, or you rely on the mirror not being perfect, and then you get your identical photons coming out. Okay? So a laser does rely on some sort of a resonant cavity based on just the multi-beam interference effects we discussed. So therefore, I am pushing to change the name, right? It should be light oscillation. Amplification isn't specific enough. It's that you're making the light oscillate in a resonant cavity by the stimulated emission radiation. That is technically what these devices are. And of course, that name has not exactly caught on. So that is a very hand-wavy description of what a laser does. Now you can go off and work out the laser physics in detail.